The worst bridge collapse deaths ever. Drawn to disaster. A bridge is an agreement between engineering and gravity. The engineering says the structure will hold. Gravity says it will try to pull it down. Every bridge standing today is a bridge where engineering is winning that argument. Every bridge in this video is a bridge where gravity won. The people who died on these bridges were not doing anything unusual. They were crossing water, crossing valleys, crossing roads. They were doing what bridges are built for people to do. These are the worst bridge collapse deaths ever. Ashtabula Bridge Disaster. Ohio, 1876. The Ashtabula Bridge carried the Lake Shore and Michigan Southern Railway across the Ashtabula River Gorge in northeastern Ohio. It was an iron truss bridge, approximately 150 feet long and 75 feet above the river below. It had been in service for 11 years. On the evening of December 29, 1876, a passenger train called the Pacific Express was crossing the bridge in a blizzard. The train consisted of 2 locomotives and 11 passenger cars, carrying approximately 160 people. It was one of the busiest travel nights of the year, the period between Christmas and New Year. At approximately 7:28 p.m., the leading locomotive crossed the bridge safely and reached the far side. As the second locomotive and the passenger cars followed, the bridge collapsed. The iron truss structure failed completely and catastrophically, dropping the train 75 feet into the frozen Ashtabula River below. The passenger cars fell onto the ice, compressed together, and immediately caught fire. The train's heating stoves, coal and wood-burning units, ignited the wooden car interiors within minutes. The combination of the fall, the crushing of the cars, and the subsequent fire killed the majority of victims. Many passengers survived the fall, only to die in the fire. Rescue workers on the gorge above could hear survivors trapped in the burning wreckage, but could not reach them quickly enough through the blizzard conditions. 92 people died in the Ashtabula Bridge disaster. 19 bodies were never recovered, consumed entirely by the fire. The chief engineer who designed the bridge, Amasa Stone, was called before an investigation committee. He maintained that the bridge had been properly designed and built. He died by suicide 4 years later. The investigation found that the bridge had been improperly designed with structural flaws that should have been identified before the bridge entered service. Quebec Bridge Collapse, Canada, 1907. The Quebec Bridge was designed to span the St. Lawrence River south of Quebec City. When completed, it was intended to be the longest cantilever bridge in the world, a span of 1,800 feet across the river. Construction began in 1900. The chief engineer responsible for the design was Theodore Cooper, a respected bridge engineer based in New York. Cooper had not visited the construction site in Quebec in over 2 years. By the summer of 1907, he was managing the project remotely, reviewing documents sent to him by telegraph and mail. In the summer of 1907, concerns were raised about the deflection, the bending, of certain compression members in the bridge's south arm. Workers on the site noticed that steel members were bending in ways that the design had not anticipated. The concerns were communicated to Cooper in New York. Cooper sent a telegram on August 27, 1907, ordering construction to stop while he reviewed the situation. The telegram arrived too late. On August 29, 1907, at 5:37 p.m., just as the afternoon work shift was ending and workers were preparing to leave the bridge, the south arm of the Quebec Bridge collapsed. The entire southern portion of the structure fell into the St. Lawrence River in approximately 15 seconds. 75 construction workers died. The majority were Mohawk iron workers from the Kanawake Reserve near Montreal, highly skilled structural steel workers who had become specialists in high steel construction. 33 Kanawake Mohawk men died on August 29, 1907. For a community of approximately 1,500 people, the loss of 33 working-age men in a single afternoon was catastrophic. The Quebec Bridge was redesigned, and construction resumed. In 1916, during the installation of the central span, a second collapse occurred. 13 more workers died. The bridge was finally completed in 1919, 12 years after the first collapse, and 24 years after construction began. Tacoma Narrows Bridge, Washington, 1940. The Tacoma Narrows Bridge was a suspension bridge spanning the Tacoma Narrows Strait in Washington state. It opened on July 1940. From the first days of operation, the bridge exhibited an unusual characteristic. It oscillated visibly in the wind, earning it the nickname Galloping Gertie from construction workers and the local public. Engineers and officials were aware of the oscillation from the beginning. Multiple reports were filed. The Federal Works Agency and the bridge's designers were notified. The response was to commission a study. The study had not been completed when the bridge fell. On November 7, 1944, months after opening, sustained winds of 42 miles per hour caused the bridge to begin oscillating with increasing amplitude. The deck began twisting along its length. The oscillation became so severe that a man named Leonard Coatsworth, a newspaper editor, was forced to abandon his car on the bridge and crawl to safety on his hands and knees as the deck tilted 45 degrees beneath him. His car and his daughter's dog Tubby, who was inside it, remained on the bridge. At 11:02 a.m., the Tacoma Narrows Bridge collapsed into the water below. The 2,800-foot center span fell in sections. Tubby the dog died in the collapse, the only fatality of the Tacoma Narrows disaster. Coatsworth survived. The Tacoma Narrows collapse became one of the most studied engineering failures in history. Film footage of the bridge oscillating and collapsing was captured and has been viewed by engineering students worldwide ever since. The collapse demonstrated the phenomenon of aeroelastic flutter. The bridge was not simply blown down by the wind, but was driven into resonant oscillation by aerodynamic forces that the design had failed to account for. The bridge's insurance policy paid out. The designers faced no criminal charges. A new Tacoma Narrows Bridge opened on the same site in 1950. Silver Bridge collapse. West Virginia, 1967. The Silver Bridge connected Point Pleasant, West Virginia, to Gallipolis, Ohio, across the Ohio River. It was an I-bar chain suspension bridge built in 1928. On December 15, 1967, it was carrying rush-hour traffic, commuters crossing the bridge in the late afternoon before Christmas. At 4:58 p.m., a single I-bar in the bridge's suspension chain failed. The I-bar, a flat steel bar with a hole at each end through which a pin connects it to the next bar in the chain, had developed a stress corrosion crack at one of its pinholes over the course of 39 years of service. The crack was 0.1 inches deep. It was completely invisible to inspection from the bridge surface. No inspection method available at the time could have detected it. When the I-bar failed, the chain on one side of the bridge lost structural integrity. The load transferred to the remaining structure, which could not support it. The entire bridge collapsed in approximately 1 minute. 46 vehicles were on the bridge at the time of collapse. 31 of them fell into the Ohio River. 46 people died. 2 bodies were never recovered from the river. Among the dead was a 37-year-old woman named Charlene Wood, who was driving home from work with 2 passengers. All 3 died in the Ohio River. A 26-year-old man named Paul Cantrell was crossing the bridge on his way to pick up Christmas presents for his children. He died in the river. His body was recovered on December 17th. The Silver Bridge collapse directly caused the United States government to establish the National Bridge Inspection Program in 1968, requiring regular inspection of every bridge in the country on a 2-year cycle. Before the Silver Bridge fell, there was no national program for bridge inspection in the United States. No standardized system existed for identifying aging infrastructure before it killed people. Fade Bridge de la Concorde Overpass, Laval, Quebec, 2006. On September 30, 2006, a section of the de la Concorde Overpass in Laval, Quebec, Canada, collapsed without warning onto the highway below. The overpass carried Boulevard de la Concorde over Autoroute 19. It had been built in 1970. A 30-meter section of the overpass fell onto the highway below, crushing vehicles that were traveling beneath it at the moment of collapse. The collapse occurred in the middle of the afternoon, on a Saturday. 5 people died instantly when the concrete fell on their vehicles. A 6th person died in hospital. The vehicles beneath the collapsed section were completely crushed by the weight of the concrete. The investigation that followed found that the overpass had deteriorated severely due to a combination of poor original construction, inadequate maintenance, and the effects of de-icing salts used on Quebec roads during winter, salts that had penetrated the concrete and corroded the reinforcing steel within. Inspections had been conducted, but had failed to identify the severity of the structural deterioration. The Johnson Commission, established to investigate the collapse, found that the overpass should have been identified for replacement years before it fell. It found systemic failures in Quebec's bridge inspection and maintenance programs. 41 overpasses across Quebec were immediately closed for emergency inspection following the Laval collapse. I-35W Mississippi River Bridge, Minnesota, 2007. On August 2007, the I-35W bridge over the Mississippi River in Minneapolis, Minnesota, collapsed during the evening rush hour. The bridge carried Interstate 35W across the river and was one of the most heavily used routes in the Twin Cities metropolitan area, carrying approximately 140,000 vehicles per day. At 6:05 p.m., during peak traffic conditions, and while construction work was ongoing on the bridge deck, the bridge collapsed. 111 vehicles were on the bridge at the time. 17 of them fell into the Mississippi River. The bridge fell in sections, with the center span dropping approximately 60 feet to the river below and onto the riverbanks. 13 people died, 145 were injured. Among the dead was a 20-year-old University of Minnesota student named Sherry Engebretson, who was driving home from work. A school bus carrying 52 children was on the bridge when it collapsed. The bus came to rest on a remaining section of the bridge deck. All 52 children survived. The National Transportation Safety Board investigation determined that the collapse was caused by undersized gusset plates, flat steel plates that connect the structural members of a truss bridge at their joints. The original design from 1967 had specified gusset plates that were too thin for the loads they were required to carry. The construction materials placed on the bridge deck on the day of the collapse, approximately 287 tons of construction equipment and materials, had pushed the already undersized gusset plates beyond their load capacity. The gusset plate flaw had existed since 1967. The bridge had been rated as structurally deficient since 1990. The inspection reports had noted the deficiency. Nobody had acted on them with sufficient urgency to close or repair the bridge before August 2007. The numbers, according to data compiled by bridge engineering researchers, at least 500 bridge failures have occurred globally since 1800. The United States Federal Highway Administration estimated in 2023 that approximately 42,000 bridges in the United States alone are classified as structurally deficient, meaning they have been identified as having conditions that affect their safety or functionality. 42,000 bridges in one country. The common thread across every collapse in this video is not extraordinary weather, not acts of nature, and not events that could not have been predicted. The common thread is a flaw that existed before the collapse, a design error, a material defect, a crack developing over decades, a maintenance failure that was either not identified or was identified and not acted upon. The bridge does not announce when it is going to fall. It stands and carries traffic and appears to function until the moment it does not. The people crossing it at that moment are not doing anything wrong. They are crossing a bridge. That is what bridges are for. If you found this video useful, subscribe for more and leave your suggestions for the next video in the comments.